Hi. So in the previous in the part 1 video of the AND gate, I have completed the design part of the AND gate. The whole code for the design part, I have explained it very briefly, line by line and word by word. The setup as well as the explanation of the design part of the AND gate, I have completed in the part 1 video. Okay, so I shall suggest you first go and check the video, the part 1 video in which the design.vhd has been explained. Then come and check this part 2 video. In this part 2 video, I will complete the whole explanation about the test bench part as well as the output. Okay, let's move towards the test bench part. Okay, so in the entity part, you can see that entity we have written, or I have written that after writing the library IEEE use IEEE.std underscore logic underscore 1164.all. This is compulsory part. Okay, you have to write this, or it will also automatically generate after clicking the Vhdl. After that, I have written entity TB. I have given a new name as TB. TB means test bench. So I have written the short form as TB. You can give any name. Okay, you have to give like TB underscore and underscore get. It's not mandatory. Like you write in the program, na. If you think as a Java, you write the program as public class, then you give a name by which the program is get saved. Like this, in the same way, we are writing as entity. Not using public class Java, we are writing as entity. If you give us public class Java AND gate, it will save as AND gate. Public class Java your name, it will save in your name only. So like this way, I have taken entity TB underscore AND underscore gate as same. This thing is same for the design also. Okay, for the better understand, I have used the gate name only as AND gate. Okay, so entity TB underscore AND underscore gate is. After that, I have not used the port, the in, the out, nothing. I closed the entity like end entity TB underscore and underscore get semicolon. Something weird, right? The entity is empty. Yes, this is true. The entity is empty. Okay, so let's explain why it is empty. Why the test bench entity is empty? Test bench entity, not the design. Test bench entity is empty. Why? In Vhdl, an entity defines the pins that connect a component to the outside world. Okay, but a test bench is the outside world. It is the top of the hierarchy. Okay, understand? Think of it like this: your AND gate chip needs pin because it has to be plugged into a circuit board, but the test bench is the entire lab. It contains the power supply, the signals, the chips, and the oscilloscope. Okay, since there is nothing above or outside the lab to plug into, the lab doesn't need external pins. It is a self-contained universe where the code creates the signals internally. Okay, that means in the test bench, the already all the things which are need to use for doing the code or doing the program, all the things are already present in the test bench only, or in your room only. So why you need the extra things, or why you need the same things again? You have the things now. You have the AND gate, you have the input, you have the output. Why shall we get or buy another, means the same input or same output, right? This will increase the storage unnecessarily, and this is the true. Okay, so that's why we have to leave this entity part as empty only. Now what happens if I do add ports to the test bench? This is one of the most important question, right? If we add, what will happen? You actually can write ports into the test bench entity without the compiler crashing, but you are creating a ghost connection. How? Imagine you are building a virtual simulation of a car engine. If you put an exhaust pipe port on the very top level of your simulation, the computer will ask, where does this pipe go? Since there is no other code outside the test bench, is not outside the test bench to catch the signal, the port just sits here empty and disconnected. In a real project, a simulator starts at the top and work its way down. If the top level has ports, the simulator has no way to drive these ports from the outside, right? So standard practice is to keep it empty. So the simulator knows everything I need is inside the file or already is present in this file. So no need to use any extra ports, okay? So leave this part. Means you have to keep it as empty only. Top of the world hierarchy. I have told you in the previous only, right? So this is the big picture. Now let's expand it. When you type the name of your test bench into the top entity box, which I have told you now that leave it right now, we will use later on. I'm telling that part. When you type the name of your test bench into the top entity box on EDA Playground, you are telling the tool start here. This is the king of the project. Start from here. Means the top entity box which is present, we have to give the name of this AND gate. Means this TB underscore AND underscore gate. We have to copy this part and paste in that entity box. Okay. So we are telling the program run from this. This is the king of the project. First run this, then we will go to the next part. Okay. Run this first. By keeping the entity empty, you are confirming that this file is the master controller. Okay. Means the things are already present. That means this is the one of the best house or best barrack house where all the things are already present, already reload. Then we need no external thing. Okay, so this has become the master controller. So it defines its own signals like TB dash A means underscore A and TB underscore B. It's already have. It is own defined. Okay, and uses them to feed the AND gate. It is the boss that doesn't take orders from anyone else, which is why it has no inputs from the outside. Okay. So when we shall run, means when we run the program, we will get the wave diagram. In that, you can see that already a input and output is generated as TBA, TBB underscore B, then TB underscore Y. This is already generated. During the after successful running the program, I will show you the output, the wave, that where is the TBA, TBB. Okay. So this is the part that why we should keep empty of the why we should keep entity as empty in the test bench part. Okay. Okay, so I have written a architecture code, that is architecture behavior of TB, means the entity name only, that the same way where I have written the design.vhd, in the same way the architecture is written in the test bench, but little bit different. Okay, there is some difference. The first thing is we see is the component declaration. This might seem like we are repeating ourselves because we already wrote this in the design file. I have told you previously, no? We have already written the architecture part, but in Vhdl this is mandatory. Handshake between files. This is known as handshake between files. Okay. Now what exactly is a component declaration is doing? Think component declaration as a page from a parts catalog. Okay, when you are building a circuit on a breadboard, you first have to look through your box of parts and find the right chip. You check the datasheet to see, okay, this chip has two input on the left and one output on the right. In the test bench, the component block is your virtual datasheet. You aren't actually placing the chip yet. You are just telling the computer, I am planning to use a part called AND gate later, and this is exactly what its pins look like. Okay, means the component part. The component, what is that? AND gate is the component, and in the later we will use the A as input, B as input, and Y as output. So we are telling the test bench that later on we will use the AND gate, means we have checked the data sheet. Okay, AND gate is written, is present, means sorry, is present. So okay, this input have to be need. So we are writing the port, we need this A, we need this B, and we need this Y. So after that we completing and closing our end components. Okay, so why do we write it? You might ask, why do I have to type this again? I already wrote the entity in design.vhd na. Why man, why? The reason is that Vhdl is blind by default, and this is the fact. Each file in Vhdl is like an isolated island. The test bench file doesn't automatically look inside the design file to see what you have built. Okay, the test bench means you are testing the design part, you have built that part, and the VHDL will not get, or by default will not see what you have done in the design, how you have designed your code. It will not see that code. Okay, so by writing the component declaration, you are giving the test bench a memory of the design. It's like a pre-flight check. You are saying, I know that there is a design out there called AND gate, and I am preparing my test bench to receive it. This strictness is what makes VHDL so reliable for massive million gate chips. Okay, so this is the part. Now what happens if we don't write it? Means it will give a unknown part error. Okay, so if you skip the declaration and go straight to typing to use the gate, the compiler will panic. It will hit your code and say error. Now what is the error? Unknown code AND gate. Don't know what is the AND gate, bro, because this is means by default it is a blind. It will not get into your design code and it will check that okay, this is the AND gate. No, it will check in the test bench only. Okay, so it's like trying to call a phone number that isn't saved in your contacts. You might know the person exists, but your phone doesn't have the link, like this. Okay, without this declaration, the linker means the part of software the glues your files together cannot find the connection. It won't know if A is an input or an output, or even how many pins the gate has. The simulation will fail before it even starts. Okay, so that's why we need this part. Okay, so let's move towards the next portion. I have written a command as inputs. So how we shall write the command? We shall write the command like we have to give 2 dash, then after that it become a command line. Okay, dash dash, then you can write whatever you want. The code means whenever you will run the code, it will not check the command line, it will just ignore it, like how the compiler do. Okay, so I have taken a signal tb underscore a colon std underscore logic colon equals to 0, then semicolon. Okay, now let's explain that what is the signal, what are signals. In VHDL, ports are like the pins on a chip. The ports are like a pins on a chip, but signals are the copper wires that connect those pins together. I've given the calculator example. The buttons are present, but wire are not present. The wire has no connection with the buttons with the skin. The one end with the button and another end with the skin. That's why the output is not showing in the skin. If you clicking on 2, the 2 is not showing. Whenever you connect that copper wire, means that wire from button to skin, then only you can see the output. Means whatever you are typing in the button or whatever you are clicking in the button, the output will be shown in the skin. In the same way, this signal is the copper wire that connect those pins together. Imagine you have a like, let's take another example. Like imagine you have a standalone AND gate chip sitting on your desk. To test it, you need to plug into a breadboard and use jumper wires to connect it. to a power source or a switch. Like, so in our code tb underscore a, after that we shall take another signal, that is tb underscore b, and another signal that is for the output, that is tb underscore y. Okay, so these are the jumper wires. They carry the electrical information from our test program, means the process, into the pins of the AND gate. Okay, means their internal connection points. The main thing is the internal connection point, this signaler. Now I have taken as colon equals to, then inside single quotation 0. Now VHDL is a very precise language. When the simulation starts at time 0, the computer needs to know is the electricity is on or off. If you don't use colon equals to, then in single quotation 0, the wire start in a state called U, which stand for uninitialized. On your waveform, this shows up as a confusing blue or red line. Okay, so by setting it to 0, you are ensuring your lab experiment that start in a safe and known state. It's like making sure all your switches are off before you plug in the battery. Okay, so this is the initialization part. It prevents the undefined states. That's why a clean start will be from the 0. Input A, the start will be from 0. Again input B, the start will be from 0. Output, it will decide by the test bench that what will be the output. Okay, we shall not define the output. So the signal tb underscore y colon std underscore logic. That's it. No need to give any initialization or any 0 1 like this. Now what happens if we don't write it? So if you don't declare these signals, you have no way to touch your component. Means in virtually, physically the IC are present, but in virtually testing, you can say in virtually you cannot touch the components. You might think that you can just drive the component ports directly, but VHDL doesn't allow that. Ports are just holes. You need a wire to plug into that hole. If you try to map your ports without having signals declared first, the compiler will say signal not found. Okay, so it would be like trying to turn on a light bulb by waving your hand near to the socket without the actual wire connecting the switch to the bulb. Nothing will ever happen. Your AND gate will sit there perfectly coded but completely unreachable. Okay, so by this we have need this tba tb, means this signal we need this. Okay, so this is the part of the signal. Now let's move towards the next part. See, something is written here. At first I have written begin, then UUT, then colon, then AND underscore gate, then again port, map. I have using another word, that is port, then map, and something is written there like A equals to TBA, B equals to TBY. Okay, now so this is one of the most exciting part of the test bench. Okay, this is the instantiation. This is where all our preparation pays off. Okay, we have defined the component, we have laid out our wires, and now it's time to build the circuit. What is instantiation? In our early steps, the component declaration was just a description in a catalog. Okay, it was a description. Okay, so this is a catalog, these are the things are present. So instantiation is the act of actually taking the component out of the box and placing it on your breadboard. These are the dataset, or the box is present where different type of like Arduino or anything is present, like chips or any ICs are present. Now it's time you are taking those chips and placing in your breadboard one by one in the ports. So in VHDL you can have one design, the AND gate, but use it in five different times in a larger project. Each time you use it, that is an instance. Here we give our instance a name as UUT. Okay, this is the instance name UUT, which stands for unit under test. This name is like a label we stick on the chip, so we can refer it to later, like this way. It marks the transition from code on a page to object in a simulation. So this is the explanation about the instantiation. Now you have seen another word is present, port map. This is the wiring instruction. Okay, wiring instruction. The port map is the most critical part of the connection. It is the wiring diagram. Now look at the syntax. A equals to greater than TB underscore A. The part on the left A is the formal part, formal port. This is the physical pin on the AND gate chip. Now the part on the right TB underscore A is the actual signal. This is the where we laid on our breadboard. Okay, so that's why we didn't take as less than equal to, we have taken as equals to then greater than. This equals to greater than symbol is the connection. You are telling the simulator, take this specific pin and solder it to the specific wire. Okay, take this specific pin and put in the specific wire. Okay, so without this map, this the simulator would have a chip and wire sitting next to each other, but they wouldn't be touching. Okay, now what happens if we don't write it? It will give a problem as missing chip. If you speak this instantiation, you can essentially trying to run a lab experiment with no equipment. Your test bench will run. Your stim proc, means a keyword is present like stim underscore proc, will send signal through the wires tb underscore a and tb underscore b, and an oscilloscope will record the results. But because there is no AND gate connected, means the AND gate uses design, that design, or you can say the port actually has been present, is not connected to those wires, the output tb underscore y will never move. It will remain dead or uninitialized, means the U, capital U. So it's like turning on the light switch in a room that has no light bulb. Okay, so you are doing the work, but there is no hardware there to respond to your action. Your simulation will be successful in that it won't crash, but your result will be completely empty. Okay, so this is the part of the begin then port map. So in the same way, I have told you that A has taken in the same way B, and for the output Y. Okay, so now we enter the process block. If the rest of our code is the hardware and the wires, this section is the human operator. Means I have written the stim underscore proc, stim proc. In the previous only I have told you. Then colon, then process. So this is the process block. This is the means this is where we decide what happens and when it happens. Okay. So at first we have written stim proc colon process. Now Vhdl means what is the process now? This is a sequential script. What is it? Sequential script. Vhdl is normally a parallel language. Everything happens at the exact same time, but a process is a special zone where Vhdl acts like a standard programming language like Python or C. So what I have told, let's repeat once again. But a process is a special zone where Vhdl acts like a standard programming language, that is like Python or C. Means inside this block, the simulator follows your instructions one line at a time. Okay, one line means line by line the instruction will be simulated in order. Okay, it's script that tells the simulator first do this, then do that, like this way. Without a process you couldn't create a sequence of events. Always remember, without a process you couldn't create a sequence of events. Everything would just happen in one big confusing flash. Okay, so what we have learned, it is a sequential execution block. It allows us to define a step-by-step story of our simulation to follow. Now we have to begin the process. Let's begin. Like in the same way, we have to write begin. After that, see, one by one, see, I have written the tb underscore a equals to, means here equals to is assigned as less than equals to, so equals to 0 means first input will be 0. Then tb underscore b less than equals to 0 means another input will be entered as 0. Then wait for 10 ns means 10 nanosecond. Now another question might arise in your head, that is, why wait for 10 nanosecond? This is known as a timeline. Okay, the timeline, the simulation timeline. In the previous I have told you now, as a simulator, a word inside this block, the simulator follow your instruction. This simulation, this is a timeline. Means this is the most critical concept for beginners, that computers are incredibly fast but hardware takes time to react. Okay, so if you tell the computer to change tb underscore a to 1 and then 0, it will do it in less than a trillionth of a second. Okay, so wait commands tell the simulator to pause the simulation clock by waiting 10 nanosecond. You are creating a window on your waveform. Means it gives the AND gate enough time to see the input, process it and update the output before you move to the next phase. Okay, means it create a simulation like time, like, okay, 0 0 is running, wait, then give the output, then shift to the next. If you did the if you don't give the wait, then it will be, means very fast the changes will be happen. So you can might get the output nicely, otherwise it can be very messy type of thing, means very small output will be shown, because trillionth times it can change. It can be fast to give the output, so we have to wait for some second, no, some nanosecond. So 10 nanosecond is the best one, waiting 10 nanosecond. Okay, in the next I have written as tb underscore a, then assign it as 0, then 1, means this is the next input, then 1 0, then 1 1, means 2, this is 2 input and get, that means 2 bit, means 2 to the power 2, that is 4. That means a b y, a consists of 0 0 1 1, b consists of 0 1 0 1, like this. Okay, so here now what happens, as in the previous only I have discussed. Now let's discuss more depth, that what happens if we remove the wait for 10 nanoseconds. It will give a blur. Means if you delete the wait line, the simulator will execute every single test case at the exact same moment. I have told you in the previous only. You might get the fresh output or not. Like imagine trying to take 4 different photos at the exact same piece of film at the same time. You wouldn't get 4 pictures, you would get a blurry mess. Means moving to next, means suppose a person is moving his head here and there, then you will not get the exact image of his, if he or she does not stop his head at a some time or pause his head at a some time. You will get a blurry type of image. So in Vhdl the last command would win, means you would only see the final test case, that is 1 and 1, and the previous case 0 0 0 1 and 1 0 would vanish instantly. Your waveform would look like a flat line, because you didn't give the simulator time to draw the changes, because it is changing very fast, no. So that's why we have to write this wait nanosecond. Now in the final we have writing as wait semicolon. So why we have to write this wait? This is the stop sign. Okay, hey, stop means the red light, stop. When the red light arrives, then the car gets stopped in the traffic. Okay, so stop. Notice the semicolon at the end of the last wait. When wait has no time value after it, it means wait forever. Okay, means when wait has no time value for it, after it means when there is no time value is present, then it means wait forever. It is the official stop sign for your simulation. It tells the computer that the experiment is over. I have tested everything I wanted to test. Okay, now just sit still and let me look at the waveform. Okay, so it freezes the simulation at that specific point in time so you can inspect the results in peace. Now what if, now another question, what happens if we remove the final wait? It will become an infinite loop. Okay, this is the hidden trap of Vhdl. By default, a process is designed to loop forever. If you don't have the final wait with a semicolon, the simulator will reach the end of your test, jump back to the top and run case 1 again and again. It will do this millions of times per second. This is called an infinite loop. It will crash your browser, freeze EDA Playground, or fill your log files with millions of identical lines. It turns a simple 40 nanosecond test into a never ending cycle that wastes your computer's power, nothing else. Okay, so it have to be give. So after that, after this we have to also end the process also. So end process, then in the architecture behavior, in the same, like the same in the design part, we have end the architecture behavioral. Here also we have to end the architecture behavior, then end process. Okay, so this is all about the test bench part. Design part is complete, test bench part is complete. Now the next part is we have to get the output. We have to run the program now. So for running the program, in the previous only I have told you, in the top entity the name will be, what will be the name? The name will be the test bench name. That is, we have given as entity as, in the test bench the entity as tb underscore and underscore get. So copy it and paste it in the top entity, or you can also write in the manual way also with the help of the keyboard, like tb underscore and underscore get. Okay, so there is no problem. Now for running, you have to move the cursor towards the upward. Here see different type of things are present as new, run, save. So click on the run button. If any error occurs, then it will show you the error, in which line it will also show you. Okay, if nothing is present, means if no error is formed, then it will give it will give as a word as done, and it will also give a writing as opening epwave dot 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 then done. After that, see, this is the wave. This is the wave diagram which we want as the output. This is the beauty. Okay, now let's dive into the waveform, this wave output. This is one of the most crucial thing. Okay, so listen carefully. So this is the wave diagram. After clicking the run button, the EP wave is in front of us. This is the waveform viewer. Okay, so why are there two sets of signals, that is tb underscore a and single a, normally a? On the left side of the viewer, you will see two groups of signals. You see tb underscore a, tb underscore b, then tb underscore y. Those are our test bench signals. But you also see single a, b and y. Those are the internal ports of our AND gate. Think of it like this. tb underscore a is the physical jumper wire on your breadboard, and a is the actual metal pin on the chip. The metal pin you have seen in the physical IC, the metal pin, the a is the actual metal pin. When you look at the waveform, you are seeing the signal on the wire and the signal at the pin simultaneously. Okay, that means the tb underscore, that portion is the signal belongs to our test bench environment, and normal a, b, y, those are the design component. Okay, the UUT part. Now why do they look exactly the same? The port mapping. In the test bench we have seen the port map we have written, where a is equals to greater than tb underscore a. We have seen that, no? So that part, so we are virtually adding that wire to that pin. Okay, because they are physically connected. They are physically connected, so whatever voltage is on the test bench where tb underscore a must also be on the gate pin, that is a. So in a complex design, this is how you debug. If your test bench wire is sending A1 but the chip pin is showing 0, you know you have a wiring mistake on your port map. Okay, so here you can check your original design code. This is the beauty of the test bench, testing your code. Now reading the output Y. Now look at the output signals TB underscore A underscore Y and Y. These are also identical because they are connected. Notice that these signals are only one speaking back to us. While we control TB underscore A and TB underscore B in our process, we have no control for Y. Remember that we have given the input as 00011011, but in Y we didn't give any input. So the AND gate logic is what drives this wave. By comparing the input wave to the output wave, we can visually confirm the truth table of our gate. Okay, so we have written the wait 10 nanosecond step, 0 to 10 nanosecond, both inputs are low. The output says 0 and 0 equals to 0 for 10 nanosecond. Then another next you can see 10 to 20 nanosecond, one input goes high and output stays low, means 0 and 1 equals to 0. 20 to 30 the output goes high, the other input goes high and output stays low, means 1 and 0 equals to 0. 30 to 40 both inputs are high, finally the output jumps high, 1 and 1. This proves our hardware logic is perfect, the waveform doesn't lie. Okay, so this is all about AND gate using the Vhdl. Okay, so this is the AND gate code and this is how you can check the output. This is the proof that your AND gate, the hardware part, is working perfectly. Okay,